All right, today we're going to demystify something you use every single day, how a computer actually thinks. We're going to follow the path from a simple human problem all the way to a program that solves it, one step at a time.
So, you gotta ask, right? At its heart, a computer is really just a very, very complicated box of on or off switches. So how in the world do we get from that simple idea to, calculating things, browsing the web, and creating art? Well, the trick is to give that machine a simple human problem to solve.
Now we're going to start with something we all get, figuring out a paycheck. I know, it sounds almost too basic, but by breaking this one task down, we're going to uncover the absolute core building blocks of how all computers work.
Okay, first things first. If we want to give our machine instructions, we can't just talk to it in English. We have to learn the only language it really understands, and that's the language of electricity.
Everything, and I mean literally everything, a computer does boils down to this one simple thing, the bit. Think of it like a light switch. It can be off, which the computer sees as a 0, or it can be on, which it sees as a 1. That's it. All the incredible stuff we see on our screens, it's all built from billions of these simple on and off switches.
Now, one little switch by itself isn't super useful, but what happens when you line up 8 of them? By grouping 8 bits together, we get something called a byte. And this is what lets the computer represent more complex information like the numbers and letters we're going to need for our paycheck.
So how does this actually work? Well, it's all about patterns. To represent the number 1, the computer just flips on that first switch. For the number 2, it uses a different switch. For 3, it's a combination of the first 2. By creating a totally unique pattern of 1s and 0s for every value, the computer can represent pretty much any number you can think of.
To translate a number, the computer basically plays a little game of does it fit. So take a number like 167. It starts with the biggest value it can, 128. Does 128 fit into 167? Yep. So that's our first one. Then it just works its way down. Does 64 fit in what's left? Nope. That's a 0. Does 32 fit? Yes. That's a 1. If it fits, it's a 1. If not, it's a 0. And just by doing that, 167 becomes 101000111 in the machine's language.
Okay, so we can talk to the machine, but for our paycheck thing, the computer needs to remember some stuff, like the hours we worked and how much we get paid per hour. We need to give it a memory.
And that's where variables come in. A variable is just a friendly name we give to a spot in the computer's memory. So instead of trying to remember that our hours are stored as, 00101000, we can just label that memory spot hours_worked. It's exactly like slapping a label on a moving box, so you know what's inside.
And yeah, there are a few rules to make sure the computer doesn't get confused. The names have to be clear and simple. You start with a letter, you avoid weird symbols or spaces. Using simple labels like pay rate or hours_worked makes our instructions perfectly clear.
Okay, so we can talk to the computer, and we've given it a way to remember things. We're getting there, but the last piece of the puzzle, the really important part, is the recipe, the exact step-by-step instructions that tell the computer what to actually do with that information.
Now, in the tech world, we call this recipe an algorithm. It sounds like a fancy word, but it's for a really simple idea. It's just a precise to-do list that tells the computer exactly what to do and in what order to solve a problem. It takes all the guesswork out of it.
So for our paycheck problem, the algorithm is super simple. Step 1, get the number of hours worked. Step 2, get the hourly pay rate. Step 3, multiply those two things together. And step 4, show us the final answer. This simple 4-step recipe makes sure that calculation is done perfectly every single time.
So what makes an algorithm work? Well, any good recipe has 3 key things going for it. The instructions have to happen in a specific sequence. There's a clear flow of control, so it always knows what to do next. And super important, it has to have a termination point. It needs to know when the job is done. Without these, the computer would just be lost, right?
All right, let's put it all together now. Let's retrace our steps and see how we went from just a question to a real machine-powered answer.
It all started with a simple, real-world problem we wanted to solve, calculating that paycheck.
Then, to tackle that problem, we had to learn how to speak the machine's language, translating our numbers into that binary code of 1s and 0s.
After that, we gave the computer a way to remember things, using those variables like hours_worked to label and hold on to our data.
And the final step? We wrote a recipe, our algorithm, that gave the computer the exact step-by-step instructions to do the math.
And all of this really gets to the heart of the matter. A computer isn't smart all by itself. Its incredible power comes from us, from our ability to give it clear, logical instructions. The magic isn't really in the box of switches, it's in the logic we feed it. So think about it. If we can teach a machine to calculate a paycheck using just these fundamental ideas, a binary language, variables, and algorithms, what's the limit? From predicting the weather to composing music, it all starts right here with these same powerful building blocks. The real question is, what are we going to teach them to do next?